Good morning, good evening, your greeting accept. The special relativity of Einstein and Poincare. Recall the principle of Galilean relativity, which tells us that the physical laws of Galileo and Newton remain totally unchanged if we pass from a stationary to a moving frame of reference. This implies that we cannot ascertain simply by examining the dynamical behavior of objects in our neighborhood whether we are stationary or whether we are moving with uniform velocity in some direction. But suppose we adjoin Maxwell's equations to these laws, does Galilean relativity still remain true? Recall that Maxwell's electromagnetic waves propagate with a fixed speed c, the speed of light. Common sense would seem to tell us that if we were to travel very rapidly in some direction, then the speed of light in that direction ought to appear to us to be reduced to below c, and the apparent speed of light in the opposite direction ought to be correspondingly increased to above c, which is different from the fixed value c of Maxwell's theory. Indeed, common sense would be right. The combined Newton and Maxwell's equations would not satisfy Galilean relativity. It was through worrying about such matters that Einstein was led in 1905, as in effect was Poincare before him, to the special theory of relativity. Poincare and Einstein independently found that Maxwell's equations also satisfy a relativity principle, that is, the equations have a similar property of remaining unchanged if we pass from a stationary to a moving frame of reference, although the rules for this are incompatible with those of Galilean Newtonian physics. To make the two compatible, it would be necessary to modify one set of equations or the other, or else abandon the relativity principle. Einstein had no intention of abandoning the relativity principle. His superb physical instincts were insistent that such a principle must indeed hold for the physical laws of our world. Moreover, he was well aware that for virtually all the known phenomena, the physics of Galilei and Newton had been tested just for the speeds very tiny compared to with the speed of light, where this incompatibility would not be significant. Only light itself was known to involve velocities larger enough that such discrepancies would be important. It would be the behavior of light, therefore, that would inform us which relativity principle we must indeed adopt. And the equations that govern light are those of Maxwell. Thus, the relativity principle for Maxwell's theory should be one to preserve, and the laws of Galilei Newton must accordingly be modified. Lorentz, before Poincare and Einstein, had also addressed and partially answered these questions. By 1895, Lorentz had adopted the view that the forces that bind together are electromagnetic in nature, as indeed they turned out to be, so that the behavior of actual material bodies should satisfy laws derived from Maxwell's equations. One implication of this turned out to be that a body moving with a speed comparable to that of light would contract slightly in direction of motion. Lorentz had used this to explain a puzzling experimental finding, that of Michelson and Morley in 1887, which seemed to indicate that electromagnetic phenomena could not be used to determine an absolute rest frame. Does matter always behave in such a way that its motion cannot be really locally detected? This was the approximate conclusion of Lorentz. Moreover, he was limited to a specific theory of matter where no forces other than electromagnetic ones were regarded as significant. Poincare, outstanding mathematician that he was able to show that there is an exact way for matter to behave according to the relativity principle underlying Maxwell's equations, so that uniform motion cannot be locally detected at all. He also obtained much understanding of the physical implications of this principle. He appears to have regarded it as just one possibility and did not share Einstein's conviction that some relativity principle must hold. The relativity principle satisfied by the Maxwell equations that has become known as special relativity is somewhat difficult to grasp, and it has many non-intuitive features that are at first hard to accept as actual properties of the world in which we live. In fact, special relativity cannot be properly be made sense of without the further ingredient introduced in 1908 by the highly original and insightful Russian-German geometer Hermann Minkowski. Minkowski had been one of the Einstein's teachers at the Zurich Polytechnical. His fundamental new idea was that space and time had to be considered together as a single entity, a four-dimensional spacetime. In 1908, Minkowski announced in a famous lecture at the University of Göttingen, henceforth space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of two will preserve an independent reality. Let us try to understand the basics of special relativity in terms of magnificent space-time of Minkowski. One of the difficulties in coming to terms with the space-time concept is that it's four-dimensional, which makes it hard to visualize. However, having survived our encounter with phase spaces, we should have no trouble with the mere four dimensions. As before, we shall cheat and picture a space of smaller dimensions, but now the degree of cheating is incomparably less severe and our picture will be correspondingly more accurate. Two dimensions would suffice for many purposes, but I hope that the reader will allow me to be a little more adventurous and go up to two space and one time. This will provide a very good picture, and it should not be hard to accept that in principle the ideas will extend without much change to the full four-dimensional situation. The thing to bear in mind about a space-time diagram is that each point in a picture represents an event that is a point in space at a single moment, a point having only one instantaneous existence. The entire diagram represents a whole of history, past, present, and future. A particle, since it persists with time, is represented not by a point but a line called the word line of the particle. This word line, straight if the particles move uniformly and curved if it accelerates, that is non-uniformly, describes the entire history of the particle's existence. In figure 5.16, I have depicted a space-time with two space and one time dimension. We imagine that there is a standard time coordinate t measured in the vertical direction and two space coordinates x over c and z over c measured horizontally. The cone at the center is the light cone of the space-time origin O. To appreciate its significance, imagine an explosion taking place at an event O. Thus, the explosion occurs at the spatial origin at time t is equal to 0. The history of light emanating from the explosion is the light cone. In two-dimensional spatial terms, the history of light flash would be a circle moving outwards with the fundamental light speed c. In full three-dimensional space, this would be a sphere moving outwards at speed c, the spherical wavefront of the light. But there we are suppressing the spatial direction y, so we just get a circle, like the circular ripples emanating from the point of entry of a stone thrown in a pond. We can see this circle in the space-time picture if we take successive horizontal slices through the cone moving steadily upwards. These horizontal planes represent different spatial descriptions as the time coordinates t increases. Now, one of the features of relativity theory is that it is impossible for a material particle to travel faster than light. All the material particles coming from the explosion must lag behind the light. This means in space-time terms that the word lines of all the particles emitted in the explosion must lie inside the light cone. It is often convenient to describe light in terms of particles called photons rather than in terms of electromagnetic waves. For the moment, we can think of a photon as a small packet of high frequency oscillations of electromagnetic field. The term is physically more appropriate in the context of the quantum descriptions that we shall be considering in the next chapter, but classical photons will also be helpful for us here. In free space, photons always travel in straight lines with the fundamental speed c. This means that in Minkowski's space-time picture, the word line of a photon is always depicted as a straight line tilted at 45 degrees to the vertical. The photons produced at our explosion at O describes the light cone centered at O. These properties must hold generally at all points of the space-time. There is nothing special about the origin. The point O is no different from any other point. Thus, there must be a light cone at every point of space-time with a significance the same as that for the light cone at the origin. The history of any light flash or the word lines of photons, if we prefer to use a particle description of the light, is always along the light cone at each point, whereas the history of any material particle must always be inside the light cone at each point. This is illustrated in picture or figure 5.17. The family of light cones at all the points may be regarded as a part of Minkowskian geometry of spacetime. The picture of Minkowskian geometry. What is Minkowskian geometry? The light cone structure is its most important aspect, but there is more to Minkowskian geometry than that. There is a concept of distance which has some remarkable analogies with distance in Euclidean geometry. In three-dimensional Euclidean geometry, the distance r of a point from the origin in terms of standard Cartesian coordinates is given by r square is equal to x square plus y square plus z square. This is just a Pythagoras theorem, the two-dimensional case being perhaps more familiar. In our three-dimensional Minkowskian geometry, the expression is formally very similar, the essential difference being that we now have two minus signs. More correctly, we should have four-dimensional Minkowskian geometry, of course, and the distance expression is. What is the physical meaning of the distance quantity s in the expression? Assume that the point in question, that is the point P with coordinates blah 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 in the three-dimensional case lies with the light cone O. Then the straight line segment OP can be represent part of the history of some material particle, say a particular particle emitted by our explosion. The Minkowskian length of a segment OP has a direct physical interpretation. It is the time interval actually experienced by the particle between the events O and P. This is to say, if there were a very sturdy and accurate clock attached to the particle, then the difference between the times is suggested that O and P is precisely as contrary to the expectations. The coordinate quantity T does not itself describe the time as made by an accurate clock unless it is at rest in our coordinate system, which means that the clock would have a word line that is vertical in diagram. Thus T means time only for observers who are stationary, that is vertical word lines. The correct measures of time for a moving observer uniformly moving away from the origin according to special relativity is provided by the quantity s. This is very remarkable and quite at variance with the common sense Galilean Newtonian measures of time, which would indeed be simply the coordinate value t. Note that the relativistic Minkowskian time measures s is always somewhat less than that t if there is any motion at all. Motion will tend to slow down the clock as compared with t, that is, as viewed with respect to our coordinate frame. If the speed of this motion is small compared with c, then s and t will be almost the same, which explains why we are not directly aware of the fact that moving clocks run slow. At the other extreme, when the speed is that light itself, p then lies on the light cone, and we find s is equal to 0. The light cone is precisely the set of points whose Minkowskian distance from O is actually 0. Thus, a photon would not experience any passage of time at all. We are not allowed to even more extreme case where P is moved to just outside the cone, since that would lead to an imaginary as the square root of negative number and would violate the rule that material particles or photons cannot travel faster than light. This notion of Minkowskian distance applies equally well to any pair of points in the space-time for which one lies within the light cone of the other, so that a particle could travel from one to the other. We simply consider O to be displaced to some other point of space-time. Again, the Minkowskian distance between these points measures the time interval experienced by a clock moving uniformly from one to the other. When the particle is allowed to be photon and the Minkowskian distance becomes 0, we get 2 points, one of which is on the light cone of the other, and this fact serves to define the light cone of that point. The basic structure of Minkowskian geometry. With this curious measures of length for word lines interpreted as the time measured or experienced by physical clocks contains the very essence of special relativity. In particular, the reader may be acquainted with what is called the twin paradox of relativity, or twin brother remains on Earth while the other makes a journey to the nearby star, traveling there and back at great speed, approaching that of light. Upon his return, it is found that the twins have aged differently, the traveler finding himself still youthful, while his stay-at-home brother is an old man. This is easily described in terms of Minkowski geometry, and one sees why through a puzzling phenomenon. It is not actually a paradox. The word line AC represents the twin who stays at home, while the traveler has a word line composed of two segments AB and BC, these representing the outward and inward stages of the journey. The stay-at-home twin experiences a time measured by Minkowski's distance AC, while the traveler experiences a time given by a sum of the two Minkowski's distances AB and BC. These times are not equal, but we find AC greater than AB plus BC, showing that indeed the time experienced by the stay-at-home is greater than that of traveler. The so-called twin paradox of special relativity is understood in terms of Minkowskian triangle inequality. The above inequality looks rather similar to the well-known triangle inequality of ordinary Euclidean geometry, ABC being now 3 points in Euclidean space. AC is less than AB plus BC, which asserts that sum of two sides of triangle is always greater than the third. This we do not regard as a paradox. We are perfectly familiar with the idea that Euclidean measures of distance along a path from one point to another. This example is a particular instance of the fact that the shortest distance between 2 points is measured along the straight line joining them. The reversal of the direction is inequality sign in the Minkowskian case arises from the sign changes of the definition of this distance. So the Minkowskian AC is longer than the jointed route ABC. Also, this Minkowskian triangle inequality is a particular instance of a more general result. The longest among word lines connecting two events is the straight one. If two twins start at the same event A and end at the same event C, where the first twin moves directly from A to C without accelerating, but the second twin does accelerate, then the first will always experience a longer time interval than they meet again. It may seem outrageous to introduce such a strange concept of time measure at variance with our intuitive notions. However, there is now an enormous amount of experimental evidence in favor of it. For example, there are many subatomic particles which decay in definite time scales. Sometimes such particles travel at speed very close to that of light, and the decay times become delayed in exactly the way that one would deduce from the above considerations. Even more impressive is the fact that nuclear clocks can now be made so accurate that these time-slowing effects are directly detectable by clocks transported by fast low-flying aeroplanes agreeing with Minkowskian distance measures as noted with T, strictly taking the aeroplane's height into account. Small additional gravitational effects of general relativity become involved, but these also agree with observation. See next section. Moreover, there are many other effects intimately connected with the whole framework of special relativity, which are constantly receiving detailed verifications. One of these, Einstein's famous formula E is equal to mc square, which effectively equates energy and mass, will have some tantalizing implications for us at the end of this chapter. I have not yet explained how the relativity principle is actually incorporated into the scheme of things. How is it that observers moving with a different uniform velocities can be equivalent with respect to Minkowskian geometry? How can the time axis can completely equivalent to some other straightforward line, say OP extended? Let us think about Euclidean geometry first. Clearly, any two individual straight lines are quite equivalent to each other with regard to the geometry as a whole. One can imagine sliding the whole Euclidean space rigidly over itself until one straight line is taken to the position of the other one. Think of two-dimensional case Euclidean plane. We can imagine moving a piece of paper rigidly over a plane surface so that any straight line drawn on a paper comes into coincidence with a given straight line on the surface. This rigid motion preserves the structure of the geometry. A similar thing holds for Minkowskian geometry, although this is less obvious and one has to be careful about what one means by a rigid. Now, in place of a piece of paper sliding, we must think of a peculiar kind of material. Taking the two-dimensional case first for simplicity, in which the 45-degree lines remains at 45 degree while the material can stretch in 145-degree direction and correspondingly squash in the other 45-degree direction. This kind of rigid motion of Minkowski space called the Poincare's motion, which may look very rigid, but it preserves all the Minkowskian distances, and preserving all distances is just what the word rigid means in the Euclidean case. The principle of special relativity asserts that physics is unchanged under such Poincare motion of spacetime, in particular the stationary observer S, whose word line is the time axis of our original Minkowski space, has completely equivalent physics to the moving observer M with the word leading OP. Each coordinate plane T is equal to constant represents space at any one time for the observer S, that is, it is family of events which he would regard as simultaneous. Let us call these planes as simultaneous spaces which we pass to another observer M. We must move our original family of simultaneous spaces to a new family by Poincare's motion. So providing the simultaneous spaces for M, note that M's simultaneous spaces look tipped up, and this tipping up might seem to be in the wrong direction if we are thinking in terms of rigid motions in Euclidean geometry, but it is what we must expect in a Minkowskian case, while S thinks that all the events on any time t is equal to constant plane occur simultaneously. M has a different view. To him, it is the events on each one has tipped simultaneous spaces that appear to be simultaneous. Minkowskian geometry does not in itself contain a unique concept of simultaneity, but each uniformly moving observer carries with him his own idea of what simultaneous means. Consider the two events R and Q in figure 5.21. According to S, the event R takes place before the event Q because R lies on an earlier simultaneous space than Q. But according to M, it is the other way around, Q lying on the earlier simultaneous space R. Thus, to one observer, the event R takes place before. Thus, for one observer, the event R takes place before Q, but for the other it is Q that takes place before R naught. This can only happen because R and Q are what are called spatially separated, which means that each lies outside the other light cone, so that no material, particle, or photon can travel from one event to the other. Even with quite slow relative velocities, significant differences in time ordering will occur for events at greater distances. Imagine two people walking slowly past each other in the street. The events on the Andromeda Galaxy, our own Milky Way, some 2,000,000,000 kilometers away, just by two people to be simultaneous with the moment that they pass one another could amount to a difference of several days. For one of the people, the space fleet launched with the intent to wipe out the life on a planet Earth is already on its way, while for the other, the very decision about whether or not to launch that fleet has not yet even been made. Two people A and B walk slowly past each other, but they have having different views as to whether the Andromedian space fleet had been launched at the moment that they pass each other. Einstein's general relativity. Recall Galileo's great insight that all bodies fall equally fast in gravitational field. Einstein's general relativity. I will continue reading it in the next video.